Hi everyone. Today we'll take a look at proof by contradiction. So from the proofs chapter, this is the final method, and we'll end with this one. So proof by contradiction is again, in my opinion, it's kind of broad because the applications can be anywhere. Like right, they can ask you prove something by contradiction, right? They can ask you to the examiner can ask you to prove multiple different mathematical concepts through contradiction, right? The whole key point which you want to take away from this video is the process. Similar exact it's exactly what I wanted to explain from the mathematical induction and the direct proof, right? Because the pool is endless, right? It's an ocean of different questions that can be asked, and the only thing you can really prepare for in this chapter is just knowing the process, right? It might not happen to everyone that it clicks at the moment, right? For some people it might not, and that's completely understandable, right? So if you just encounter a wide variety of questions, and see how contradiction is being used, that's like more than enough to prepare for this part. Okay, so before I get started with a few example questions, I just want to, reiterate the entire process of what we're going to do, right? In theory. So the first thing is we're given a statement, right? We are given a statement, right? And the first part of this is that we assume that it's false. Okay, that's the first thing we do, right? So if I have, for example, I have an example, let me just word it like this. And I say example, if P then Q. Okay, so my first assumption would be assume that if P, then not Q, right? This is what I've changed up, right? From Q to not Q. This is the key point. And essentially, what this does is that now we have this new assumption or this new expression that we're going to work with. And we're going to be solving this, further and further and further. And what's going to happen is, in the end or towards the end of our entire solution, we're going to run into a barrier. And when we run into this barrier, right, we can't move any forward. And upon on this barrier, we can say that we have hit a contradiction, right? Or it's not possible, and hence the original statement is true and our assumption is false. So I'll just rewrite it down, just write down what I said. So uh, upon solving, we run into a barrier, right, which prevents us from moving forward. And so that's our contradiction. Okay, so the first example question which I'm going to take is a very mainstream question, and you probably have seen it everywhere on the website on Google, and your teacher's probably taken this as well. But I'll just, if for those who haven't learned it in class yet, and haven't seen it anywhere, I'll just take this example just because it's a very mainstream one. All right, so the first one that I'm going to take is prove by contradiction that square root of 2 is irrational, right? This is the question that we're given, right? Now, honestly, I don't think any of the square root type of questions will ever come in the final exam because they're so mainstream, right? Every textbook has them, every teacher explains them, every website has them, that the IB just won't bother asking you this because you're probably gonna have this memorized by now. So, nevertheless, let's just do it for the sake of understanding. So, when we have the word irrational written here, what does it mean, right? Just try to revise those definitions that you learned about rational, irrational, whole numbers, natural numbers, real numbers, imaginary numbers, all those things, right? So the first few properties of irrational, right? So when we think of irrational, right, the properties that should come in mind, they're like non-repeating and non-ending, right? Non-ending. numbers, right? So for example, pi, right? We have pi, or we have e, right? These are irrational numbers because they go on and on and on, right? They go on and on, and their numbers don't repeat. It's not like they're like 1 point. It's not like they're 1.22222. No, they go on and on, right? So now you might say, oh, you know, 1/9 is irrational. No, it's not. It's 0.11111. The one goes on forever, so it's repeating. So now let me bring this. If a number is rational, right? If a number is rational, it can be written. Sorry, it can be written in the form p by q. Okay, p by q, right? Can be written, and where this is a simplest fraction, right? Yeah, right, simplest fraction. So it's a simplest fraction, and it cannot be simplified anymore. It cannot be simplified anymore, right? So that's the form of any rational number, right? This is a rational number. It follows this p by q. We can even have a whole number, right? 20. We can write 20 by 1. We can write 40 by 2, right? These all rational numbers can be written in this form, right? So now let's go to the first part of the contradiction that we have, right? The first part of a contradiction that we had was what? So it said that to assume that if something is given, we take the opposite of what's given, right? So we say that square root of 2 is irrational. So we assume, so let's write it here, step 1. We assume square root of 2 is rational. So when we say something is rational, it can be written in this form, right? So square root of 2 is equal to p by q. Right? Where p by q is a fraction in the simplest form that has no more common factors together, right? The highest common factor is essentially 1 between them, right? So now, what can we do to move forward, right? We have to run into some sort of barrier. We know that. We're trying to run ourselves into some sort of a barrier. So let's square both sides. Let's get rid of the square 2, right? Square root of 2. There's absolutely no need for that. It's completely garbage. So what are we left with? We have 2p squared by q squared. 2 is equal to p squared by q squared. Let's move q squared on the other side. So we're left with 2q squared is equal to p squared. Now here's an important relation that we have. What this says is 2 times q squared. Q squared can be any number. It can be an odd number, an even number, right? And oh yeah, just one more point I want to make sure, right? P and Q are integers. So Z, right? They're integers. They're not decimals. They're not any sort of, numbers. They're integers. Okay? So it's an integer being squared, right? So it'll give us an integer. So it can be any integer. It can be odd integer or an even integer, right? Because you can't really have fractional integers. That doesn't exist. Okay, so we have 2q squared, right? So whatever q squared may be, we don't care. We know that this whole number is even, right? We know 2q squared is even. So therefore, p squared is also even, right? So what we can deduce from this is p squared is even. And therefore, p is even. Now you might be like, whoa, where did you get this from, right? How can you say this with so much confidence? Just think about it, right? You have 16. Or you know what? Let's take 16, right? 16 is 4 squared, so 4 is even. We have 144 is equal to 12 squared. That's 12. 12 is even, right? We have 100, right? Which is 10 squared. That's even. What else do you need? Like we can, this is actually a fundamental understanding, right? And it's okay if this just clicked here right now, because anyways you're just learning, right? So you can keep this in mind when you move forward. So we have p is even, right? So now let's rewrite p in a different form. So let's say p is equal to 2 times some k, which is some k constant. Okay, Now, if I rearrange this, right? If I put 2k for p, what do we have? We have 2q squared for p, which would be 2k whole squared, right? And then we have 2q squared upon 4k squared. Then q squared is equal to 2k squared. So it's quite similar. We're coming back to the same original situation that we had here, right? It's quite similar. So now we have, this is even, right? For the same reason. Therefore, q squared is even. Therefore, q is even. So now we can say q is also some multiple of 2p, right? Let's take another constant, 2p, right? So now we kind of run, now here's the contradiction that what I'm going to bring out. So we have p is even and we have q is even. So when something is even, they have a common multiple, right? When something is even, they have a common multiple. That common multiple is 2, right? Any number that is even is some number multiplied by 2. So if q is even, it's some number and it's multiplied by 2. If p is even, it's some number multiplied by 2. So what we can say from this, right, is that p and q have a common multiple of 2, okay? Of 2, right? Which means they're not simplified, right? And this is our contradiction. Hence, contradiction. And because of this, right, they have some common multiple. And we had worked with the assumption that it's a rational number, p by q, where p and q are in their simplest forms. They cannot be simplified anymore. Yet, we're finding, yet we look at this, we're getting that this is an even number, and they have a multiple of 2. Right? This is completely off from what we're just working with, right? And this is disproving the statement, and it's disproving the fact that square root of 2 is rational. So it's because if it's disproving the fact that square root of 2 is rational, thus square root of 2 must be irrational, right? And this is it. This is the entire question. It might, if this is the first time you're seeing it, you might be like, what just happened, right? Right? Like I just did some weird thing right here made by p by q, and then I got, so I said that they have a common multiple, and then all of a sudden I'm saying, oh, the original statement which the question said is true, and what the heck is going on here? I'm just completely blind, right? I just don't understand anything. Like whatever just happened on the screen right now, I just like completely, it's gone, right? That's exactly what happened with me as well. I was so confused, right? But you have to understand that you're following just a simple set of rules and assumption, right? Just your normal mathematical rules, but you're starting with the assumption, right? And therefore, because of your mathematical rules, your assumption is deemed as false, right? And because it's deemed as false, your original condition is true, right? Your original condition right here is true. Okay, so I'll just do one more question similar to this, and let's change the color before that. So let's go with orange. And let's say that we can say that prove by contradiction that square root of 3 is irrational. And if you did understand the previous example, you should try pausing the video and doing it on your own, because the all process is basically the same, right? There's nothing that changes what we did in square root of 2 and square root of 3, right? So go ahead, pause the video, try it, and come back. Okay, so let's try this, right? So we're given that square root of 3 is irrational. Now, again, following the same principles and same steps, we make the first assumption that assume that square root of 3 is rational. Now let me tell you something. If you have a question, right, of proof by contradiction in your exam, and it's some wild, bizarre stuff that you're getting, right? And you're completely lost. You're like, what do I do with this, right? First thing that you do is you don't waste your time, right? What you do is you don't dwell upon it too long. You see it. If you think you can do it, go for it. If you can't, don't do it, right? Because there is no time limit on how quickly and how quickly you can grasp the situation and solve it, right? So, but the one thing that you should do before moving on to the next question is just write the statement. Assume that square root of 3 is rational or something. If p by q, then write if p, then not q, right? Write the opposite of the statement, because I'm pretty sure you can get 1 mark just right off the bat, right? That's a simple, easy mark with, effortless, right? You don't have to do anything, just have to write the opposite statement. So always write the statement and then move on to the next question. Don't leave the entire paper. Don't leave the entire question blank. Is that what I'm saying? So now back to this question. Square root of 3 is rational. Okay. So therefore we can write square root of 3 is equal to p by q for the same reasons that we did for square root of 2, right? Where p by q is a fraction in its simplest form, does not have any more common factors. The highest common factor, however, is 1, right? And that's the highest common factor. Otherwise, there's nothing there. So let's do what we did in the previous thing. 3 is equal to p squared by q squared. So we have p squared is equal to 3 times q squared. So we have now from this, we have p squared is a multiple of 3. So we have p squared is a multiple of 2. Therefore, p is a multiple of 2. Or actually, I wrote p is even, and then q is even. But I can also write multiple of 2 here. Multiple of 2. And same thing goes here, and same thing goes here. Right? That's the same thing. So I can write, therefore, p is a multiple of 3. Right? And you can check this out on your own, right? So if you have 9, right? 9 is a multiple of 3. So is 3, right? Square root of 9 is 3. Let's take another one. Let's say we have 81. 81 is a multiple of 3. So is 9, right? Nothing changes. It's the same principle that's being followed everywhere, right? Again, this might be, for some of you, it might be a first time realization. It was for me. I didn't realize this until I studied this part. So it's okay, it's fine, no problem. Now you know, so just remember it. So now we have that p is a multiple of 3. So we can write p is equal to 3 times some constant. So let's rewrite it. If we rewrite it, what do we have? We have, we have 3k whole squared is equal to 3q squared. And then we have 9k squared is equal to 3q squared. So q squared is equal to 3k squared. So again, like the question like in the question we had for square root of 2, we have a similar situation here as well. So now we're doing the exact same thing. Nothing changes in this question as well. So we're saying that q squared is a multiple of 3. Therefore, q is a multiple of 3. Right? Now here's our contradiction. Our contradiction is that we assumed, right, that p and q are in their simplest form. Right? We assume that they're in their simplest form, and they don't have the highest common factor, right? Let me just rewrite it here. Highest common factor is 1, right? But here we're getting that both are multiples of 3. Both p and q are multiples of 3. Therefore, p by q is not simplified, right? It's not simplified. It's a contradiction, right? It's not, or I'll just end it. It's not rational. Therefore, p by q is not rational, right? That's how. This is all that you need to answer a question like this. But like I said before, I highly doubt the IB is ever gonna ask, to prove that a square root of some number is rational or irrational, just because there's, it's the first example that all teachers use. It's the first, it's the most common example of for contradiction on any website. Go on Google, just go on any math website, that you'll see, a working very similar to this, right? And an explanation very similar to this. Math is very objective, right? If you remember, if you know from your TOK lesson, right? Math is very objective, although it has multiple methods. The end result is always the same, and it can never be disagreed upon, right? So this was, again, square root of 3. So now let's look at another example, which is a little bit more different. All right, so let's look at this example. Proof by contradiction that p squared minus 8q minus 11 is equal to 0. Okay, so let's try to draw some sort of a relationship, and then, sorry, a big mistake. It said it's not equal to 0, right? So again, first step, right? Never leave the step, right? Always, always, always do the step. Assume that p squared minus 8q minus 11 is equal to 0. All right, and this is the contradiction. If I didn't mention this before, this is the contradiction, right? So what can we do? How can we move forward? Let's. So what we can do is we can say p squared is equal to 8q plus 11, right? We just move this here. We have some sort of a relationship, right? Let's see. Now, what I'm going to do is here, again, these steps are probably something that won't come to you immediately, right? So it's fine if you're like, why didn't I think of this? It's completely fine. This part is something, where a lot of things won't, click, and you just have to you'll figure them out as you do, as you look at different solutions and as you look at different questions. So what I'm going to do here, I'm going to break this 11. I'm going to break it into 10 and 1. So what I'm going to write is I'm going to write 8q plus 10 plus 1. Right? Now, what I'm going to do is I'm going to factor a 2 out here. I'm going to write 4q plus 5 plus 1. Now, if you remember, if you did watch my video on direct proofs, you might remember how we denote even and odd numbers, right? And if you take a look at this closely, this entire thing is an odd number. Because see, whatever 4q plus 5 is, we don't care, right? We don't care. Oh, and just so I mentioned, p and q are integers, right? I usually forget to mention that, but yes, they are. So don't assume that they're fractions or some other numbers at all, right? They're p and q are integers. So 4q plus 5 can be anything, and we don't care what it is, right? For all we know, they can be minus a million, whatever. Doesn't matter, right? Because they're being multiplied by 2 at the end, so they're going to become an even number, right? Whether this is odd or even, right? So 2 multiplied by an odd number is still an even number, and 2 multiplied by an even number is also an even number. So regardless of what happens, this is an even number. But when we add something plus 1 to that even number, we get an odd number, right? If you remember that, right? If you remember in my previous video, I wrote 2k plus 1 maybe, or 2n plus 1, and even is always 2k, right? So now we know that p squared is odd. And if p squared is odd, p is also odd. And you can think about it anyway. You can take any odd number and square it. So 9, for example, 9, 25. Let's see. What else can we think of? 81, for example. They're all odd numbers, and their square root is also odd. So now we have this relationship. P is an odd number. So how do we denote an odd number? Usually, we denote an odd number by saying P is equal. So let's denote it that way, right? So we can say P is equal to 2k plus 1. All right, because it's an odd number, we don't care what it is. We're just working with a bunch of variables, and we're going to continue to, right? So let's plug it in right back in this original equation. So what do we have? We have 2k plus 1 whole square is equal to all the stuff right here, right? I'm going to use this part, not this part. This is a little hairy. I don't need that much. So let's use this part. What do we get? 8q plus 11? 8q plus 11. Right, let's open this up. What are we left with? 4k squared plus 4k plus 1 is equal to 8q plus 11. Let's bring the 8q here. Let's take the constant there. What do we have? 4k squared plus 4k minus 8q is equal to 10. Right? Let's simplify this a bit more. So we have 2. Let's divide both sides by 2, right? So we have 2k squared plus 2k minus 4q is equal to 5. Now, I'm going to do something I'm going to do one more step here. I'm going to factor out a 2 from here. So what am I going to have right here? I'm going to have k squared plus k minus 2q is equal to 5. Now, if you have been paying attention throughout this entire solution, you might be like, hold up. There's a contradiction right here. I have some here, some integer value, right? We don't care what it is. It's being multiplied by 2. Therefore, this entire part is even, right? I don't care what this is. It's being multiplied by 2, so it has to be an even number. But we have a 5 here, and 5 is an odd number. So LHS, our left-hand side, does not equal our right-hand side. And therefore, we have contradiction. Hence, contradiction. And that's where we stop. The moment we can say we have a contradiction, we can just stop, right? We can just stop and we can end it right here. So I'll just, reiterate all the steps that I did, right? Again, you might be like, what just happened? Some of you might be like, what just happened? Because you might have understood how the square root of 2, square root of 3 thing works, and now you have something completely different. And I just did a bunch of steps that would have never clicked, I would say, never striked your mind, right? But it's okay, it's fine. I'll just reiterate the steps that I did, right? So first, I drew up a relationship of p squared, right? By shifting around the variables, right? By manipulating them. I like saying that. So I manipulated things around here, and I determined that p squared is odd. So p is also odd, right? Then I changed up the relationship of p. I wrote it as 2k plus 1, right? It's some integer, 2k plus 1, because that's how all odd integers are taken as. Thereafter, I put it back in as p, right? So I changed up some variables, and then I expanded it. Upon expanding it, I got all the variables to the left-hand side, all the constants to the right-hand side, right? Then I factored out a 2, got this side essentially, which stated that it's an even number, but the right-hand side said it's odd. And this is where, I stopped, because that's not true, right? And I got into a, place of contradiction. So and then therefore, that's it. I can't move any forward. I shouldn't move any further because I have a contradiction. And therefore, my previous statement right here, p squared minus 8q minus 11 does not equal to 0. This is actually true. All right, next question. We have prove by contradiction that 12a squared minus 6b squared does not equal 0. Okay, so let's try and see what we can do here, right? So we have first step, again, never leave the step even if you don't get it, right? Assume that 12a squared minus 6b squared is equal to 0, right? We just did the opposite of what it is, right? Now let's solve this around. So we have 2a squared, I just divide both sides by 6, is equal to b squared equal to 0. And then we'll have 2a squared is equal to b squared. And then let's see if I can do something like this. B squared by a squared. So now I have, and if I, simplify this a bit more, what do I have? Square root of 2 is equal to b by a. Now your brain might start working here. You might be like, hold up. This is very similar to the situation when we were trying to prove that square root of 2 is irrational, right? Because what we did was we first assumed that we were given that it's irrational, and then we assumed that it's irrational, and then we wrote it in a similar form, right? We wrote it in a p by q form. However, what we got from that assumption was that the assumption is completely false, right? So what we decided that since square root of 2 is irrational, let me write it here. Since square root of 2 is irrational. It cannot, right? It can't be written in P by Q form, right? So this cannot exist. Cannot exist, right? And if this cannot exist, B squared by A squared, we have a contradiction right here, right? Hence, we have a contradiction because we just assumed, right? Our assumption hit a barrier. And the barrier was that square root of 2 cannot be written in the form of B by A because it's irrational. Cannot exist because I'll just write B slash C. Square root of 2 is irrational. Let me rewrite this. My handwriting's not that great. So, irrational, right? That's what we have. So, therefore, this is incorrect. Therefore, this assumption is incorrect. And thus, we have a contradiction, which means that our original situation is true, right? Again, you might have if you try this on your own, maybe it might have clicked to you, but if it didn't, again, slightly a different variation, right? At least this part was, and then we were actually using our previous knowledge to prove this part. So maybe you can expect something like this in the IB exam, where they don't directly ask you for determining whether square root of 2 is rational or irrational, but you end up coming here, and thus you use your information to move forward. Just one more thing I would like to mention before we do move on to the next example is I think I forgot to put it here, where A and B are integers, right? Again, I keep forgetting to do that. Sorry. But yeah, just so you don't, so the question will always mention this, right? Every IB question or the textbook question that you do will mention it, so you don't need to worry about it. But I just jotted this part down, and then I forgot to jot this part down. So next question, right? So we have prove by contradiction, or let me change the color before that. So we have, let's take purple, or let's take peach for that matter. Prove by contradiction that m squared minus n squared does not equal 1. And this time we have m and n are positive integers. Okay, m and n are positive integers. So try this question. I pause the video and try this question, and then if you take 10 minutes, take 15 minutes, take even 20 minutes, doesn't matter, and try to get somewhere where basically your assumption, your assumption would technically be m squared minus n squared is equal to 1, right? And then try to hit a barrier, try to on purpose try to hit a barrier, and then at that point you can stop and you can prove that the original given statement is true. All right, assuming you've given a go at it, let's try this, right? So now keep this in mind, right? I'm telling you right now that this is a huge important, it's an important detail to keep in mind when we move forward, because this is the part which is going to create the contradiction. Okay, so m squared minus n squared, right? Let's work with the first step, right? Always write the first step down, regardless of whether you can solve the question or not, right? So first step, assume that m squared minus n squared is indeed equal to 1, right? Let me just write it. This is equal to 1. So if you remember your a squared minus b squared form, right, which is equal to a plus b times a minus b, let's write it that way, right? Let's simplify this. M plus n into m minus n is equal to 1, right? So now, if two numbers are being multiplied and they equal 1, there can only be two possible scenarios, right? So I'll write case 1, right? The case 1 is that both numbers are positive. Let's write it that way. Both numbers are positive. Or case 2, both numbers are negative, right? So either we have plus plus, or we have minus minus. And that's the only way you can get 1, right, as the final product. So let's try this out. So if m plus n, and also one more thing, right? Either they're reciprocals of each other, right? Either m plus n is equal to 1 upon m minus n, or they're just 1 with each other, right? They can be reciprocals, but reciprocals kind of seem unlikely just because of the nature of how the thing is, how the situation or how the expression is. So let's work with the fact that we have this is 1 and this is 1, but whether it's plus or minus 1, we don't know, right? So we say that m plus n is 1, and we have m minus n is 1, right? This is our first case. And I'll do it in a different color just because it's all peachy now. So we'll take aqua, right? We'll take aqua. So we have m plus n is equal to 1, and we have m minus n is equal to 1. So now I can write this as m is equal to 1 minus n, and I can write this as 1 is equal to 1 plus n, right? And if I equate both of them together, what do I get? 1 minus n is equal to 1 plus n. 1 cancels out, and n is equal to 0, right? And if I plug in m is equal to 0, I get m is equal to 1 in both equations, right? Now, this necessarily did not really help what we have. No problem. Let's try with the second case. I'll take the second case in, not purple, I'll take beige. Okay, so next case, what we have would be m plus n is equal to minus 1, and m minus n is equal to minus 1. Right? Now, you can see this contradiction kind of right here, right? We were given that m and n are positive numbers. So, in what world are the sum of two positive numbers a negative number, right? Whether you take 1 and 1, it's 2. 1 plus 10, 11, right? Any sort of that situation, right? So you can see that we have a contradiction right here. No sum of two positive numbers is ever a negative number, right? Well, obviously this can be possible, right? But if n is greater than m by 1, then obviously you can have m minus n is equal to minus 1. But sum of two positive numbers can never be a negative number, right? That was a click that should hit you right in the within the second you write this, right? Wait, hold up, this is not possible. Okay, now let's move a little bit forward, even if we have to, right? Suppose it did not forward. Suppose you're just following the old arithmetic method, and you're solving blindly. What would happen then? All right, you would have m is equal to, my bad, m is equal to minus n minus n minus 1 minus n, and then you would have here you'd have minus 1 plus n, right? And if we equate them, what do we have? Minus 1 plus n. So we have this is canceled. Sorry, the minuses are canceled. Minus ones are canceled. So we have this. Sorry, we have minus 1, right? So this was canceled. This was canceled. So we have 2n is equal to 0 and n is equal to 0, right? And now if you plug in 0, what do we have? M is equal to minus 1. All right, let me write it here. M is equal to minus 1. And this is our contradiction, right? Because we were told that m and n are positive integers, right? They're positive integers. M can't be a negative number. And this is our contradiction. Hence, contradiction. And the moment we write this, we stop, and that's our answer. This is our entire solution. We don't really have an answer in this situation since it's a proof. We just have a solution or a working, and we can stop our working right here because we have hit a contradiction or a roadblock, I would say. And yeah, that's about it. So again, this was the final question for proof by contradiction that I wanted to share with you guys. And again, proof by contradiction might probably be the most awkward looking one, right? And it was for me as well because it was kind of new, right? It's okay. You can try. If you didn't get them, I highly recommend that you watch the solutions of these videos again, in this video again. And then what all I can really say is just do a different type of questions. And oftentimes, methods might differ in the sense of how I got this. I mean, you could have just stopped right here and said, okay, hence contradiction. But oftentimes the uncertainty, which a lot of people, I myself, lived with, was the fact that is my solution, or is my working the correct way to prove, to answer, or to prove, right? So what you can do is, I guess, you can ask your teachers. Go to your teachers and say, hey, I did this question, for proof by contradiction, and I'm not sure whether my solution is correct. So can you please check over it and let me know if this is an appropriate solution. So that way, at least you have a confident. You're confident that, okay, if I'm given a completely new question, right, completely new concept or a situation, that I can work and show a decent enough working where I can get almost all the mark, close to all the marks, if not all the marks, right? Because oftentimes you need to have a lot of confidence within yourself that, hey, I know I'm doing this correctly, right? And I know this is correct, and I know this is correct, and therefore I can get, if this question is worth 6 marks, which I'm pretty sure it is, probably shouldn't be worth more than that. I can get all the 6 marks, right? Again, kind of awkward. You're gonna have to do a lot of questions with this, but personally, in my opinion, is that if you do 10, 15 questions from the textbook, whether it's Oxford, Pearson, Hayes, whatever, just leave this chapter and move on to the heavy chapters like calculus, trigonometry, and those chapters, because that's where a lot of questions do come from. And plus, again, there's a lot of uncertainty with this question, right? Whether you'll even be able to solve a question like this, whether a question like this will ever come in the future, it's quite of uncertain. But a question from trigonometry, or a concept in trigonometry, is definitely certain. So, what I meant to say is that do this chapter for the sake of doing this chapter, right? Understand to where you can understand it. Don't push yourself, and then forget about it. And the only time ever you're going to solve a question like this is when you practice in past papers, right? Otherwise, don't even think about proofs, or don't even think about proof by contradiction, in my opinion. Proof by mathematical induction, you can do a few more questions as practice, because oftentimes they do deal with a lot of different algebra and different concepts which you might want to practice. But otherwise, you can leave this chapter and forget about it, essentially, until you're doing different past papers. So yeah, this was all for proofs, and with this video we end with the proofs chapter. And yeah, we'll see you in the next one. Bye bye.